This is part 2 of our integrated rate laws lesson. And so for the integrated rate law, the last part of the video stopped at the second order. So let's look at our zero order integrated rate law and the characteristics of it. Zero order integrated rate laws, if it's a zero order, what that means is it has a constant rate. So the rate is not going to change with the concentration. So far, we have determined that for a reaction, A yielding your products, if it were zero order, your rate law would be rate equals K times concentration of A to the 0 power. And that means, remember, anything raised to the 0 power equals 1. So rate equals K times 1, and so rate equals K. So if it's a zero order rate law, this is your differential rate law we're looking at here, you would have the rate equals K. So the rate again does not change with the concentration. So the integrated rate law, the corresponding integrated rate law for this type of reaction, a zero order, is concentration of A at time equal to T equals negative KT plus the concentration of A at time equal to 0. Again, this is still in the slope-intercept formula, y equals mx plus b. If a reaction is zero order, a plot of y versus x, so that's concentration of A versus time, will reveal a straight line with a negative slope and a y-intercept of b. The half-life of a zero order reaction is calculated by taking the initial concentration of A and dividing it by 2K. Again, K is your rate constant. So the graph of a zero order, you would have plotted concentration of A versus time, and you would end up getting a graph with that's not very straight, sorry, with a negative slope. Straight line. Pretend that's a straight line. All right, so let's look at sort of an example of how you would analyze your data. Zero orders, you would plot time versus concentration and get a linear graph. Now, for the zero order, you would get a negative slope. Again, time's always your x value you're plotting. Concentration of the reactant is your y value here. For first order, you would be plotting time as your x factor and the natural log of the concentration to get a linear graph. First order also has negative slope. Both of these have negative slope. Second order, you would be plotting time as your x coordinate and the inverse of the concentration to get a linear graph. Second order has a positive slope. So this is a typical kind of problem, and there is a rate laws program that you could download from the TI Texas Instrument website. But if you just do a linear regression on your graphing calculator, that also works. So here is typically what the data table will look like. Notice you have time and concentration. So the reaction for this would be like H2O2 was your reactant yielding products. And so we're going to be asked to determine what the order of the reaction is from the experimental data. Notice instead of rates, which is what we saw with method of initial rates with our differential rate law, this data table is showing you time in seconds and the concentration in molarity or moles per liter. So the problem says find the integrated rate law and the value for the rate constant, K. So if we look at time versus the concentration of the hydrogen peroxide, If you were to plot and do the linear regression for that particular set of data, this is what your graph would look like. So again, on your Y value, you would have plotted concentration of H2O2. And then on your X axis, you would have plotted time, and that's in seconds. Okay, and this is in molarity. Now, this is not a straight line, so that's why you would discard that. That would not be the proper order. If you look at your linear regression results, you get, this is your linear regression analysis here, and you'll notice your R squared and R values are very different. You are typically what you'll do to determine is you look at the R squared and R values, and you want to pick the ones that are closest to 1. All right, so let's look at what if we plotted time versus the natural log of H2O2. So this would be testing for first order. So notice the time values are still the same, but we have to take the natural log of the concentration. So these are the values that you get if you do natural log of H2O2 concentration. So this is testing for first order. The linear regression result for this, and again, you plotted natural log of concentration of H2O2, and then this is time. Notice you get a nice straight line if you look at your linear regression results. You get 0.99978, and you get negative 0.99999. Notice how close these are to each other and very close to 1. This one's going to end up winning out, but let's go ahead and look at the final. If you plot 1 over the concentration versus time. Okay, so here's this testing for second order. They took the inverse of the concentration. These are the values for if you take the inverse of the concentration. The time values are still the same. Time and 1 over the concentration of H2O2 was plotted. Notice how this is not a straight line. If you look at your linear regression results, your R squared and R values are not closest to 1. So based on the linear regression results, the winner here is time versus natural log of H2O2. So as a result, we see this as a first order reaction. So the differential rate law would be rate is equal to K times H2O2 to the first, okay, so, because it's the corresponding differential rate law since we verified its first order. The integrated rate law would be natural log of the concentration of H2O2 at time equal to T equals negative KT plus the natural log of H2O2 initial. And now, so what about the rate constant? The rate constant, y'all, is equal to the slope, and it's always a positive value. So the first method, you could calculate the slope from the time versus natural log of H2O2 table. And so we get our slope is negative 8.32 times 10 to the negative fourth inverse seconds. But remember, the constant is positive, so you take the positive value for that. It's just the slope that's negative. Okay? So K is equal to 8.32 times 10 to the negative fourth inverse seconds. The second method is to look at your linear regression analysis, and you can get your slope off of here. Notice A is your slope, and there's our value for the slope for the rate constant. It's the positive value, though, 8.35 times 10 to the negative 4. Here is a final summary of all of the 0, first, and second orders. So you may want to pause the video and just kind of fill in this information. This summarizes everything that we've talked about in these 2 lessons. That's it for this lesson.